So good evening, everyone. We will be starting shortly in 10 minutes. We'll wait for everybody else to join. Okay. So we'll start. So good evening, everyone. So I welcome you all to this sixth week of the this NPTEL course. Myself, I am Varak Dau. I am a doctoral student at the Department of Chemical Engineering, IIT Kanpur, and also a PMRF fellow. So as a part of my TA duty, I will be taking these questions and I will be solving approximately around 15 to 20 questions each week. So I welcome you all to this sixth lecture of mine. And let us start. We will begin. Okay. So we'll begin from the last class in which we had left two questions in because of the time was over. So we'll be starting with that. And the first question is this question. Okay, a class has 25 students. Okay, 25 students, and what we need. So last class basically dealt with the probability because that is very important as we go further into the course. So we'll be solving the remaining question. So the question is a class has 25 students, and what we have to find is what is the probability of at least two classmates. Okay, remember, at least two classmates have the same birthday. Okay, that means minimum two classmates has to have the same birthday. It can be two classmates, it can be three classmates, it can be that all 20 classmates have the same birthday. So we have to calculate the probability. So what we can do is it will be what, one minus probability of nobody has same birthday. No two students have the same birthday. So that is the how we can find it out. So what we have to find is the probability that at least two classmates have the same birthday. Okay, and I will give you a couple of minutes to solve the question. I'll give you a couple of minutes to solve the question, and I hope the question is clear to everyone. If anybody has any doubt, they can ask, and or if nobody has any doubt, they can start solving the question. So I'll shortly discuss the solution also. So there are no options for this question, so you can treat them like a numerical questions. Okay. So anybody has any doubt? So if nobody has any doubt, you can start solving the questions. I'll give you a couple of minutes. So anybody has any doubt? Anybody was able to solve it? Okay, so I'll start with the question. So the question solution goes like this. So first I'll give the answer. The answer is this 0.5837. Okay. So anybody has this? Anybody got this answer? Okay. So we'll start. So how we will start is like I said, if we start taking the probability of, as it has been mentioned, at least two. So we can have two classmates having the same birthday or three classmates having the same birthday, or two, it can go on. So instead of calculating probability for each of these events, instead what we can do is we can calculate the probability of two students of none of the students having same birthday, and one minus of that will be the probability of having at least two classmates same sharing the same birthday. Okay, that is what we are going to do, because it will be comparatively easier to compute. Okay, so that is what. So if you first compute the probability q that no two students have the same birthday. Okay, no two students have the same birthday, then the quantity which we want is two students having the same birthday is nothing but one minus probability of no two students having the same birthday, right? So what we will, instead of trying to compute this at least two student classmates having the same birthday, what we'll do is we will compute this q quantity, that is the probability of no two students having the same birthday, and one minus that will be the answer which we seek. Okay, the probability that a second student does not have the same birthday as the first is 364 by 365, right? What we have to do 1C35, right? Which will be what? What? 1 minus. Right? Sorry. Uh, it will be 364, right? No, it will be with this. Okay? So it was the problem. It will be this, right? 364 by 365. The probability that a second student does not have the same birthday at the first, because we have chosen, let's say, the first student we choose. First student has, let's say, birthday. So in how many ways the first student can have birthday? In 365 ways, right? So the second birthday can have in 364 days, because we have to remove the first, right? First, the day selected for the first student, right? Okay, so the probability that the third student has a birthday different, okay, different than either of the first two is 363 by 365, right? We have to exclude the two. So, first birthday, birthday of first student and birthday of second student, right? And so on, right? So it will be a multiplication of this. It is like a sequence problem in which each possible birthday is one card down out of the barrel. Probability that no two students have the same birthday is this one, right? This is for the second student, this is for third student, like then it will go on, right? So in factorial notation, when you do this, what we will get is this expression, right? N factorial by n minus m factorial into n to the power n, where n is in 365. So using Stirling's approximation, which is x factorial is nothing but x by e x, right? Or in other words, is x factorial ln of x factorial is nothing but x ln x minus x, right? That means if we rearrange it, ln x factorial is equals to ln of x to the power x minus ln of e to the power x, right? That means x factorial is nothing but x to the x by e to the power x, right? This is what we have, right? This is nothing but, in other words, what we can write, x by e whole to the power x, right? This is nothing but x factorial, right? So this is what we have gotten here, right? So we re-substitute it, and then using this expression, what we can use n factorial, we can approximate like this. So using this, n factorial will be what? So here x is n. It will be n by e to the power n. Okay. Then n minus m factorial will be what? It will be what? Here x will be n minus m e whole to the power and minus m, right? And okay, and n to the power m will remain as n to the power m, right? So collecting, so using this we got this, and using this we got this, right? So collecting together terms in E and dividing the numerator and denominator by n to the power n will give us this, right? This expression. And now what we do, we just put n equal to 25, n equal to 365, and m is equal to 25. Okay, so then it will be what? Q is equals to t to the power minus 25, okay, divided by 1 minus 25 to the power 365, right? Whole to the power n is 365 minus m, which is 25, into n to the power m, which is 365 to the power 25. So when we do the calculation, we end up with q is equals to 0.4163, and what we needed, like we said here, what we needed is 1 minus q, right? What we needed was 1 minus q, right? 1 minus q, which is nothing but 1 minus 0.4165, which is nothing but 0.5836. Okay, so in what basically what then did this means, there is a better than 50% chance that two students will have the same birthday. Okay? Anybody has any question? I'll wait for a couple of minutes if anybody of you have any questions. And those who do not have any question, if they want to write, they can write the solution. I'll give a couple of minutes. Oh, I think I did not share this. Oh, I'm sorry. I did not share the screen. Okay, so I will go again on this question. I will again solve this question. Okay, so we'll again solve this question. Okay. Okay. So what we have is, the question is, a class has 25 students. Okay. And what we need is, what is the probability of at least two students? Right? At least two classmates have the same birthday, right? So this will be nothing but 1 minus probability of no two students having the same birthday, right? So this is what we are doing. So if we first find the probability q that no two students have the same birthday, then the quantity which we want is nothing but probability of two students having the same birthday is nothing but 1 minus, right? So so then we focus on, rather than finding p, what we focus on finding value of q. So how do we find value of q? So q will be the probability that a second student does not have the same birthday as the first one is the birthdays, right? Because we have to exclude the date where first student has the birthday, right? So subsequently, what the probability that the third student has a birthday different than the either of the first two is 365, 363 by 365, right? And so on. So this will go on. So it's like a sequence problem in which each possible birthday is one card drawn out of a barrel, the probability that no two people have the same birthday out of m people is this one, right? So this is a probability that second student does not have the same birthday as first. This is the probability that the third student does not have the same birthday as the first two. This is the probability that the fourth student does not have the same birthday as the first three, so on and so forth. So when we write it in the factorial form, it comes out to be this. Now here what we have is n is 365 and using Stirling's approximation. So what is Stirling's approximation? So Stirling's approximation in this form is nothing but this x by e whole to the power x, right? So how did it come? So we know that Stirling's approximation is ln x factorial is nothing but x ln x minus x, right? So we write it like ln x factorial is nothing but ln of x to the power x minus ln of e to the power x, right? That means ln of x factorial is nothing but ln of x to the power x by e to the power x. That means x factorial is nothing but x to the power x by e to the power x, which is nothing but x by e whole to the power x, right? So this is what we have it here, okay? We write it in this factorial, right? That means n factorial, instead of x, you put n. So n factorial will be what? N by e whole to the power n, right? So this is what, instead of here x, we put n minus m. So what we have is n minus m by e whole to the power n minus m, and n to the power m remains the same, okay? So then we rearrange it, right? Collecting all the terms in e and dividing the numerator and denominator by n to the power n, right? So what we get is, we get this expression. Now we just, if we put, now we just have to put in the value that we have number of students at 25 and the number of days at 365. So we write, so we substitute this in this and this also in this. We end up with q. So this was what probability of no two students having the same birthday, but that is not what we want, right? Like we see it said initially, what we wanted is probability of two students having the same birthday, right? This is 1 minus q. What we do is, we do p will be nothing but 1 minus q, right? 1 minus q, where q is this. We put in the value, we get p is equals to 0.583. What does this mean physically? This physically means that there is a better than 50% chance that two students will have the same birthday, right? So does anybody of you have any doubt? If nobody has any doubt, then I'll give you a couple of minutes to write it down. And if anybody has any doubt, they can ask, okay? Yeah, nobody has any doubts? Yeah, we'll move on to the next question. The next question is this, okay? So what we have is, okay, a protein may contain several of several cytosines, okay, which may pair together to form a disulfide bond, okay, as shown in figure, okay. So if there is an even, so here it should be even, okay, even number of n of cytosine, n by 2 disulfide bonds compound, right? So if we have 2, so there can be one bond, right? Like this. So how many bonds? 2 by 2, right? So if we have 3, how many bonds we can form is 2, right? So this will be what? And maybe one like this. Oh, sorry. Okay. So if there are n molecules, we can have n by 2 bonds, right? When n is even. Okay. So let's say, okay. So how many different disulfide pairing are possible? So for our visualization, a figure has also been given that this disulfide bonding configuration with pairs 1, 6, 2, 5, 3, 4 is one of the many possible pairing, right? So these are the sulfide bonds, right? The sulfide atoms, right? And the bonding is between 3 and 4. 2 and 5 and 6 and 1. So what, how many we have? 6 sulfur, 6 cytosines we have. This is one cytosine, 2, 3, 4, 5, 6. And how many bonds we are able to form is 3 bonds, right? Which is nothing but 6 by 2, which is nothing but 3, right? So this is just for visualization. So what we have is how many different disulfide pairing arrangements are possible for this when we have n cytosines and n by 2 bonds can form. Okay, so this is the question. I hope the question is clear to everyone. If question is not clear, you can ask. And for those who have, for whom the question is clear, they can start solving. I'll give you a couple of minutes. Okay, so nobody has any questions. So I'll give you a couple of minutes for you to solve. Okay. So anybody has any answer? The answer is this one, right? Possible number of arrangements are this. Does anybody of you have any answer? Okay, then we'll solve. Okay. So the number of individual sulfide groups along the chain. The first sulfide group along the sequence can bond to any one of the other n minus 1, right? One can bond to any other n minus 1. Okay. This removes two sulfides from the consideration. Okay. The third sulfide can bond to any of the remaining n minus 3, right? Because first two are already bond. So for first, there are n minus. So if there are n molecules, we choose first one. So first one can bond to n minus 1 base, right? So then once it is bounded, two molecules are gone, right? That means the remaining are n minus, right? So the n minus, this is what here. So remaining once the one bond is formed, n minus 3 molecules are remaining. Okay. For okay, and then once that is also formed, then what we have, four sulfide atom are removed from the consideration because two bonds are formed. That means four molecules are gone. The fifth can now bond to any one of the remaining n minus 5 sulfides, etc. until n by 2 bonds are formed. Thus, the total number of arrangements of disulfide bond is the product of n by 2 terms, which is this one, right? Right. So this is, so when you simplify it, what you get is this only. Okay. Another approach. So this is approach one, right? Another approach is this one. Okay. Another approach gives you an expression that is easier to calculate. Okay. Consider placing the sulfide in a sequence. The first place may be occupied by any of the n sulfide, right? The second place by any of the n minus 1 sulfide. The third by any of the n minus 2 sulfides, and so on and so forth. Thus, if each sulfide were distinguishable from any other, then there will be n factorial arrangement. However, each sulfide has a mate from which it cannot be distinguished, right? Hence, we must divide by a factor of 2 per bond to correct for indistinguishability of the two ends of each bond. Finally, since we cannot distinguish any of the n by 2 bonds from any other, we must also divide by n by 2, hence n by 2 factorial. Hence, it will be what? Total number of possible arrangement divided by n by 2, because atoms are indistinguishable, and whole to the power n by 2, right? So when you simplify it, you get with the same expression. Okay. Although these two equations were derived in very different ways, they are numerically identical, right? And though these two do not look the same also, but numerically they are identical. So anybody has any doubts? I'll give you a couple of minutes if anybody has any doubts. Okay. And the next will be a question in which we will try to understand why do gases. Next question will be why do gases exert pressure? Right? You must have seen that gases exert pressure, but why is that? So that is fundamentally we will see from statistical mechanics point of view. I will be connecting the dots. Okay. Before that, if you have any questions, you can ask. I'll give you a couple of minutes. Okay, so nobody has any question. So we'll move on to the next question. Okay. So what we have is we want to understand why do gases exert pressure. Okay. So let us try to understand using this. Okay. So what we have is three particles are distributed, right? So we have three gaseous particles, and these are distributed in this way, right? In case B, so this is case A, this is case B, this is case. Okay. So let us try to read it then. A lattice model. Okay. So we will try to understand why do gases exert pressure using a lattice model. Right. So we have also seen a similar question in the last class wherein we had a one dimensional grid and we were to put molecules in that grid, right? So a lattice model. So imagine a gas of n spherical particles that are free to distribute throughout either a large volume or a small volume. So we have a, let's say a let's say a room, and the room is filled with a gas, and there are many cases in which first case is that we have put in the partition and divided the room into two. We'll see it. Okay. So what? Imagine a gas of n spherical particles that are free to distribute throughout either a large volume or a small volume. So we have a bigger. Okay. So why does the gas incense stick? Even if you burn it in the one corner, or when you spray perfume, even if you spray it on the one corner, you are able to get the smell in the other corner. That is because of the process called as a diffusion, right? You can say pressure also. Okay. So why does gas spread out in a large volume? The tendency to spread out is called a pressure, and it can be explained either in terms of mechanism or maximum multiplicity, right? Maximum multiplicity means maximum number of ways of distribution, right? So these are the two different perspectives on the same process. So according to the mechanical interpretation, pressure results from particle banging against the container walls, right? In general, few problems can be solved by mechanical approach. The multiplicity perspective, which we are going to talk, is more powerful, particularly for complex problems. We illustrate the multiplicity per particle here. So let's miniaturize the problem. So our aim is to devise a model that can visualize easily and solve exactly, and that will capture the essence of the problem without mathematical complexity. So this figure we are talking about shows n equal to 3 spherical particles spread out in the 5 boxes, right? First case, a and 2, 3, 4, 5, right? In a smaller volume B. Okay. So that is container A, container B, and bunch up against the left wall in one dimensional lattice in box C, right? Okay. So we take volume M, the number of lattice sets in which particles are distributed, as the degree of freedom, right? So M of A, because there are 5 boxes, we have M of A as 5 in case A. In case B, it is 4. So we have M of B is equal to 4. And in case C, it is M of C is equal to 3. So what value of M maximizes the multiplicity? So you can compute the multiplicity of n particles in M lattice. Okay, the same way we count the number of distinguishable sequences of n heads in M coin flips, right? That is, the sequence is just a set of binary outcomes, just like coin flip sequence. Our premise is that every sequence is equally likely, no matter how its vacancies and occupancies are arranged. The number of distinguishable arrangements of vacancies and occupancies of n particle in M side is, and this is nothing but M factorial into n factorial by, right, M minus n factorial, right? So we have WA is 35, so we put in the values. Okay, so this will be M, right? So it will not be like this, it will be n factorial, right? So for this case, we filed a multiplicity, it comes out to be 10, right? For case B, it comes out to be 1, right? Sorry, in case B, for case A, it comes out to be 10. For case B, it comes out to be 4, right? And in the case C, it comes out to be 1. Okay. The multiplicity increases as the volume increases. If the system has only 3 possible volume available, then the probability is PC is 1 by 50, right? That the particles will be bunch up on the left hand side of the container. Okay. So PB is nothing but 4 by 5, that the gas will expand to an immediate degree, and probability of A will be 2/3, and the particles will be fully spread out. If the degree of freedom of the system is its volume, the particles will spread out into the larger possible volume to maximize the multiplicity of the system. This is the basis of called as pressure, right? Because if we have less number of boxes, that is lesser volume, the number of ways of arrangement will be lesser as compared to when we have larger volume, right? And we all always know that in any case, we have to maximize the multiplicity. So maximizing the multiplicity would mean maximizing the number of boxes. That would be maximizing the number of volume. That is why when you have a smaller room, or when you have a larger, when you have a smaller room or smaller container, if you somehow make the volume bigger, then the particles will spread out. This is nothing which is called as pressure, right? So I hope the using this fundamental the way in which I have explained, you are able to find the solution, right? You are able to understand fundamentally why pressure exists, why gases exert pressure, right? So I'll wait for a couple of minutes if you have any doubt. If you do not have any doubts, I'll give you, those who do not have any doubts and want to write it can write it. Okay, so I'll give you 5 minutes. Okay. So nobody has any questions? So I'll give you a couple of minutes if you want to think about it or write this down. Okay, so we'll move on to the next question. Okay, so for Gibbs Donan, okay, so what we have is for a Gibbs Donan equilibrium. Okay, the initial concentrations of solution 1, that is alpha phase, is 3 millimole, and the solution 2, that is the beta phase, is 3 millimole per liter of NAP. Okay, the membrane is impermeable to P, so assume equal volumes and the pressure necessary for osmotic equilibrium, right, is applied. So there are no water fluxes, so the equilibrium concentration of ions in mole is what? So these are the options. So I'll give you a couple of minutes to solve. Okay, so anybody has any doubt, any answer? So the correct answer is option A, right? Right. Let us start. So that assume that X be the true number of moles that move from phase alpha to phase beta, that is phase 1 to phase 2. Okay. So at equilibrium, we know using this Gibbs-Duhan equilibrium, we know that this is going to remain the same, right? And alpha concentration of sodium in alpha phase multiplied by concentration of chlorine in alpha phase is going to be equal to concentration of product of concentration of sodium in beta phase multiplied by concentration of chlorine in beta phase, right? So let's say that we can write it like this, that Na alpha, let me write it like this. Let me write here. So Na alpha plus Cl alpha equilibrium Na beta plus Cl beta, right? So initially how many we had? 3, right? 3, 3, 8. This is also 3, this is also 3. So x got converted, 3 minus x, 3 minus x, 3 plus x, right? And this is, I think, 0, right? So this will be x, right? So it will be what? 3 minus x multiplied by 3 minus x is nothing but 3 plus x into x, right? Right, using this expression, which is nothing but this, right? Okay, so then you do what? Then you multiply. So when you multiply, is nothing but 3 minus x square is equals to 3x plus x square, right? This is what? 9 plus x square minus 6x is equals to 3x plus x square. So x square gets cancelled. And we rearrange, we get 9x equal to 9. This implies x equal to 1. That means final concentration will be 3 minus 1, which is nothing but 2, of Na. This is nothing but 2. Then 3 plus 1, which will be 4, and x, which is nothing but 1. So it will be N alpha is going to be this, which is nothing but 2. Cl alpha is going to be 3 minus x, which is 2. Na in beta phase is nothing but 3 plus x, which is nothing but 3 plus 1, which is 4. And Cl beta is nothing but x, which is nothing but 1. Right? So the correct answer is option A. Right? Anybody has any doubt? If anybody has any doubt, they can ask. Otherwise, those who don't have any doubt and want to write this down, they can write this down. I'll give you a couple of minutes. So nobody has any doubt. So we'll move on to the next question. This is really a theoretical question, right? What we have for Donan equilibrium condition in very dilute, okay? In very dilute solution, activity of a solvent is 1. Then activity of the solute is equal to what? Pressure, concentration, temperature, and volume. So I'll give you a couple of minutes to solve it. The correct answer is option B, right? Concentration, right? Okay, anybody has any doubt? Okay, then we'll move on to the next question, okay? So in order to, next question is also theoretical one, okay? So in order to observe the solubility of dense gas mixture, it is important to include the correction terms because it will not capture the non-ideality, it will not capture the non-ideality, it deviates from ideality, it will capture the non-ideality, or all of the above. Which of the following options is correct? So I'll give you a couple of minutes to solve. The correct answer is option C, right? It will capture the non-ideality. Obviously, correction terms will always most likely capture the non-ideality, right? So anybody has any doubt? If nobody has any doubt, then we'll move on to the another theoretical question, which is also very easy. The more, or you can even write not more, most studied potential model for fluids is my potential Sutherland potential, Buckingham potential, or Raynaud potential. So I'll give a couple of minutes to think. Okay, so anybody got any answer? Correct answer is obviously it's going to be Raynaud score. What is LJ potential? It is nothing but 4 epsilon sigma by r to the power 12 minus sigma by r to the power 6, right? Right, so this is the attractive part, this is the repulsive part, and when you plot energy versus distance, so it will come out to be like this, right? Right answer is option D. So we'll move on to the next question if nobody has any doubt. Okay. So the next question is the pressure is calculated by Viral equation, right? So Viral equation as 4.8 from the pressure calculated from the Viral equation is 4.80 atmosphere for some gas. For 1 mole of okay, so gas is also the carbon dioxide. For 1 mole of carbon dioxide gas contained in the volume of 5 liter at 300 Kelvin, calculate the second Viral coefficient. Okay. So the second viral pressure calculated using the second viral, using the first viral coefficient is 4.8 atmosphere, and we are given the mole of carbon dioxide, the volume, and the temperature. And what we are asked to find is we are asked to find the second viral coefficient. Okay, so the volume calculated using viral equation is given. Okay, so these are the options. I'll give you a couple of minutes to solve. Okay. Okay. So anybody got any answers? The correct answer is option A, 126. So we'll start. So what we are given is this is the virial equation, right? Z is equals to PVM by RT, which is nothing but 1 plus B by Vm square plus C by Vm square. So Vm here stands for molar volume. Okay. So using the above connection, that is above equation, but only involving terms up to second virial coefficient, that is up to T here till only. So when we do and we rearrange it, we get pressure as this, right? But we are given the pressure is 4.8. So we just substitute the values, known values, and we end up with this, right? So how we do it? So Z is equals to this. Okay. So answer is 126. Okay. So if anybody has any doubts, they can ask. Otherwise, we'll move on to the next question. But before that, I'll give you a couple of minutes to write this down. If anybody of you should write it down. Okay. So nobody has any doubts. So we'll take next question. Okay. The next question is a bit theoretical question. So what is we have is at 30 degrees Celsius, the solubility of ethane and acetylene in N-octane was about the same. Okay. However, at the same temperature, the solubility of acetylene in dimethyl formaldehyde is different. What could be the possible reason for it? Use your knowledge of intermolecular process. Okay. So the possible, so these are the options. Acetylene has acidic hydrogen, ethane has acidic hydrogen, acetylene has no acidic hydrogen, or none of the above. So I'll give you a couple of minutes to solve the problem. Okay. Okay, so anybody got any answer? So correct answer is option A. Okay. Acetylene has acidic hydrogen, right? So what is acetylene? Right? This is acetylene and ethane. This is H2. This is H2, right? So acetylene has acidic hydrogen. The solution is acetylene has acidic hydrogen while ethane does not. Acetylene can thus form complex with dimethyl chloride, explaining its higher solubility. No complexing occurs with octane. That is it. Okay. So anybody has any doubt in this question? So I'll wait for a couple of minutes if you have any doubts. Otherwise, we'll move on to the next question. Okay. 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 So nobody has any doubts. So we'll move on to the next question. Okay. So consider a container of fixed volume V and temperature T having N1 moles of gas 1. We now add isothermally. So isothermally is the word which has to be carefully used to this container with N2 moles of gas too, and we observe that the pressure rises dP. Assume that the conditions are such that volumetric properties of the gases and in their mixture are adequately described by viral equation, neglecting the third and higher coefficient. The second viral coefficient of pure gases are known. The expression for B12 will contain which of the following terms? Whether it will have B11, B22. So B11 represents a viral coefficient for first gas, for pure component 1, pure component 2. So both or none. So this is a theoretical question. You can use your knowledge of understanding of intermolecular and attractions to find the solution. I'll give a couple of minutes to solve. Right? So anybody got any answer? The correct answer is obviously option B, right? We have a derivation for that, okay? Let the initial pressure be P1 for N1 moles of gas at constant T and V. Okay, so then we can write this viral equation of state, right? For component 1, which when rearranged gives this. We just multiplied by V by N1 RT, right? N1 RT by V on both the sides. So let the final pressure be P2 after addition of N2 moles of gas 2 at same T and V. So what we have P2 is nothing but number of moles has increased by V, okay? And this goes to B, is where N1 plus N2 whole square multiplied by B is nothing but, so this term is nothing but this one, N1 square B11 plus 2 N1 N2 B12 plus N2 square B22. Right? So pressure change is nothing but P2 minus P1, right? So this term minus this term, right? Means this term minus this term, which is nothing but when you do the rearrangement, when you do the solving, we get this as N2RTV into 2 times N1 N2 into B12 plus N2 square B22 into RT by V square. Okay. So when we solve for B12, what we get is B12 is nothing but this. So here you see that the only term is B22. There is no B11, right? The correct answer is option B, right? B22. So if you have if anybody of you any doubt, you can ask. And so for those who wants to write, they can write. So I'll wait couple of minutes for you to understand. Okay. So nobody has any doubt. So we'll move on to the next question, right? So this is a theoretical question, okay? For a large molecule in a solution, osmometry and light scattering provide information of intermolecular forces through which chemical forces, potential of mean force, magnetic force, or none of the above. So I'll give you a couple of minutes to solve. Okay, so correct answer is option B, right? Potential of mean force. So the next question is also a theoretical question. The assertion that all fluids having the same eccentric factor have the same reduced temperature and reduced pressure is given by which theory? One parameter corresponding state, two parameter corresponding state theory, three parameter corresponding state theory, or none of the above. So I'll give a couple of minutes to think about it. So anybody has any doubt? Any answer? The correct answer is option C, three parameter corresponding, right? So we'll move on to the next question. The next question is, following second viral coefficients have been reported for a mixture of gases 1 and 2. So it's a binary mixture at temperature of 350 Kelvin. So B11 has been given this, B22 has been given as this, B12 has been given as this. And what we are asked to find is, we are asked to find molar volume of a mixture for a binary. The mixture is binary and the molar concentration of first mixture is 40 mole percent and the other is obviously 0.6 mole percent in a mixture at temperatures of 350 Kelvin and pressure of 10 bar. So these are the options. So I'll give you a couple of minutes for you to try. So anybody has any doubt? Any answer for this? Let us see. The correct answer is option C. Okay. So we'll start. So we have a binary mixture of A and B, and we know that the mixing rule is this, right? B mix is y1 square b11 plus 2y1 by2 into b12 plus y2 square b2, right? We are given that it is 40% mole percent A, and therefore mole percent of B will be 1 minus zero point 0.4, that is nothing but 0.6. So then using this information, we are given the individual viral coefficients and we are asked to find the B of mixture. So when they be using this, we calculate the B of mixture using this formula and known values. We put in this expression and then we find that B mixture is nothing but this. The viral equation, we know this is the viral equation, right? 1 plus B dash P, and then volume, we just rearrange it using, okay, so let me just, right? We just rearrange it. What we get is B is nothing but this, right? We rearrange it for B of mixture and then we get this expression and then we'll put the values of the known values into this expression and we get as V mixture is nothing but 2112711.9 centimeter cube per mole, right? The correct answer is option C. Okay. So if you have any doubt, you can ask, and if you don't have any doubt and you want to write it down, I'll give you a couple of minutes to write it down. So nobody has any doubt, so we'll move on to the next question. The next question is similar to previous question also. Consider a bi consider a binary mixture of species one. So consider a binary mixture of species 1 and 2 which obeys Barrel equation of state at 150 degrees Celsius and at 85 bar. At 150 degrees centigrade, second Barrel coefficients are given by B11 as this and B22 as this. At infinite dilute condition, let's say Y1 tending to 0. Okay, what is the molar volume of the mixture, right? So these are the options which they have. So I'll give you a couple of minutes to try. Okay, so anybody has any answer? The correct answer is option A, right? So what we have is we have a mixture of A and B. And since y1 is equal to 0 and y2 is equal to 1, because we have y1 tending to 0, right? Infinite value. So hence we know this for expression. So we put b1 y1 is equal to 0. We are left with only this expression, and hence y2 is also going to be 0. So it's going to be b mix equal to basically 0 plus 0 plus 1 square multiplied by b22, which is nothing but b22, right? Right? So we get b mixture is nothing but this, right? So then we use the functional form of the viral equation. So we know that this is the functional form. We can write it like this. B dash is nothing but b mixture by RT. So we put in the known values, right? So we put in the known values, we get this expression, and we get the volume as this, right? Which is nothing but option A, right? So I'll give you a couple of minutes to write it down, and if you have any question, you can ask. Right. Nobody has any doubt? Then we'll move on to the next question. Okay. So the next question is this. What we have in this question is the vapor pressure of a substance can be estimated from the relation, right? This is nothing but Antoine equation, right? Where P set is in torr and temperature is in degree centigrade. The value of Antoine is constant from benzene are, so these are the Antoine constant. Critical temperature and critical pressure of benzene are is in bar. So what we want to do, we want to find the eccentric factor, right? So I hope the question is clear to you everyone, and I'll give you a couple of minutes to solve it. Okay, so these are the options. Right? So everybody got it? The correct answer is option B, right? 0.21. So what we have? We have been given the Anthony constant, right? We are also given the critical pressure and critical temperature. So using this, what we do is we calculate the temperature, right? Using this expression, right? Using these expressions, we P set is nothing but this, right? We will convert it to bar, and this is the expression for eccentric factor, right? Because PC is T at T by TR is equal to 0.7, we calculate the T, right? At 0.7, hence we multiplied by 0.7, right? So putting in the known values into this expression, right? P set becomes this in bar and PC becomes this and T by TR is nothing but this, right? That means we calculate T for this, right? Using this -1 is equal to nothing but this. It turns out to be 0.2, right? I'll give you a couple of minutes to solve it. If you have any doubt, you can ask. So nobody has any questions? So then we will move on to the next question. So the next question is this. What we have is the law of, it's a theoretical question. So the law of corresponding states for all fluids following the same equation of state, sorry, the law of corresponding states for all fluids following the same equation of state states that which of the following is true, right? Critical temperature and pressure, all fluids have the at same critical temperature and pressure, all fluids have the same critical volume. Or this is option A. Whether it is option A is correct, option B is correct, option C is correct, or none of this is correct. So I'll give you a couple of minutes to think about it. Okay. So the correct answer is option B, right? Reduced temperature and reduced pressure, all fluids have the same critical reduced one, right? So anybody, correct answer is option B. So anybody has any doubts? I'll give you a couple of minutes, and then we'll move on to the next question. Okay. So nobody has any doubt. So we'll move on to the next question. Okay. So the next question and today's final question is, what is the molar volume of a gas at 400 degrees centigrade and 10 atmosphere if it obeys van der Waals equation of state? The critical parameters, critical temperature and pressure has been given. TC is, so TC stands for critical temperature and PC stands for critical pressure. So critical temperature is 120.6 Kelvin and critical pressure stands for 28 bar. So what we have to find is we have to find molar volume of gas with van der Waals equation. Okay, van der Waals equation of state. So I'll wait for a couple of minutes for you to solve. Okay. So the correct answer is option B, right? Correct answer is option B. So what we are given is pressure at 10 atmosphere, which is nothing but 10.1325 bar, and temperature is 673 Kelvin. Critical temperature has been given as this. And critical pressure has been given as this. So as we know that the van der Waals, the gas obeys van der Waals gas, we know that the compressibility factor at the critical conditions for van der Waals gas is 3 by 8, right? So using this expression, what we using the equation of state for van der Waals at the critical point, what we get is we get the critical volume as this, right? Then we use this expression of reduced pressure to find the reduced volume as this one, right? So reduced volume, VR is nothing but, so we'll write like this. So reduced volume is nothing but actual volume divided by critical volume. So actual volume is what we want. We will multiply VR multiplied by VC. VC, this is what VC we calculated, right? So we take the product of those two things. What we get is this, right? So anybody has any doubt? So I'll wait for a couple of minutes if anybody of you have any doubt.